Before viewing the rest of this video, please read Chapter 7, Confidence Intervals. What does the following statement mean? A new drug yields a statistically significant reduction in arterial blood pressure compared to placebo with p less than 0.05. The statement suggests the new drug reduces arterial blood pressure, but we do not know by how much or whether this reduction is clinically relevant. So how can we quantify the treatment effect? And can we estimate the true difference of the population means? Only when the null hypothesis is true will the t-values follow a t-distribution centered around t is equal to 0. When the null hypothesis is not true, the t-values follow a distribution centered around t prime not equal to 0. So how can we redefine the t-statistics so that it will always be centered around 0 regardless of the validity of the null hypothesis? We can redefine the t-statistics as the difference of sample means minus the true difference in population means over the standard error of the difference of the sample means. Thus, when the null hypothesis is true, it becomes a standard t definition because the true difference in population means is equal to 0. Mathematically, this means that t is equal to the difference in the sample means minus the difference in the population means all over the standard error of the difference of the sample means. Remember that the standard error of the difference of the sample means should come from the pooled variance of the two samples. So we will never know the exact value of the difference in the population means, but we can find a highly probable range of values for it. Our redefined t-value follows a t-distribution. Thus, there is 100 times 1 minus alpha percent probability that the value of t will fall between minus t alpha and t alpha. Thus, we can find the 100 times 1 minus alpha percent confidence interval for the difference in the population means as follows. Therefore, given a set of samples, we can estimate a 95% confidence interval for the difference in the population means. Another set of samples result in a different 95% confidence interval. And shown on the graph on the right are a number of different 95% confidence intervals from different samplings of the two different populations. We cannot be 100% sure that the true value of the population means, or the difference in their means, will fall within the estimated confidence intervals. However, we can be sure that this will be the case 100 times 1 minus alpha percent of the time. Therefore, the higher the confidence, the wider our interval will be. Given the 100 times 1 minus alpha percent confidence interval for the difference in the population means, if the interval does not include 0, then we can reject the null hypothesis with p is less than alpha. If the interval does include 0, then we cannot reject the null hypothesis. We can also test a different hypothesis. For example, whether the difference in the means is equal to d mu. The 100 times 1 minus alpha percent confidence interval for the difference in the means is still defined as, however, if the interval does not include du, then we can reject that hypothesis that the difference in the means is equal to du with p less than alpha. If the interval does include du, however, then we cannot reject the null hypothesis that the difference in the means is equal to du. We can also estimate the 100 times 1 minus alpha % confidence interval for a population mean. Recall that the standard error in the mean is just a standard deviation over the square root of the samples. If we go back and look at the results of the t-test in which we compared the test scores from two different sections, in which the only difference in the two tests was the time or the amount of time they had to take the test, you can see the results of the t-test in which it gives t, the degrees of freedom, and then the p-value of this t given the degrees of freedom. It also gives a 95% confidence interval. This is the same confidence interval in which we just received the background information. Thus, based on the random test scores that I used to generate for section 1 and section 2, the true difference between the means of these two sections lies with 95% confidence within this interval from minus 16 to minus 1.7 or 1.8 points. Because the confidence interval does not contain 0, this would suggest that the null hypothesis is false and that there is a true difference between the two means of the two sections. If I now go back and look at the names associated with my t-test results, I find the statistic, and that is my t-statistic, the p-value, which is my p-value here, the confidence interval, which has both confidence intervals, the estimate, and these are the estimates of the mean of section 1 and the mean of section 2. Thus, if interested, I could plot the difference in the two sections, or the means of the two sections, and then the confidence interval of that difference in the means. As an example then, I will show as a vertical plot, for example, I have an x-coordinate, say 0, and delta, which is going to be my difference in the estimate of the first one minus of the second one. And so here I have then, at some 0 coordinate which I plugged in, I have a difference between the two means of about 9 points. I can make this a little more formal. So if I set delta equal to the difference in the two sections, I can then plot again with the confidence interval. And this is actually a two-step process. So I'll plot 0, delta, and I will define the limits because I want to be able to plot the confidence interval within this plot as well. So I will use the confidence I'm also going to fill in this point, so I'm going to define the style of my point. And if I wanted to, I could further go on to label my axes. Okay. So now, to include my confidence interval, I'm going to use the arrows function, in which now I have the same x-coordinate with my confidence interval one and my second confidence interval and I'm going to declare the length equal to 0.1, angle equal to 90, and the code is equal to 3. So in my plot function, I have to define an x-coordinate, and then my y-coordinate is the difference in the means. I define the range of my plot such that it will include the confidence interval associated with this difference in the mean. This point setting defines a filled in circle, essentially. But you can try other numbers to show or to see what the other possibilities are. The arrow function connects a line between 2 points. And the 2 points that we defined were 0 and the first confidence interval, this point here, and 0 and the second confidence interval, which is this coordinate here. For this, the length is 0.1, and this refers to the length of this arrow here. The default is 0.25. The angle I define as 90 degrees to make it have the appearance of an error bar, for example. But the default here is an angle of 30 degrees to make it look more like an arrow. The code is equal to 3, defines this as a double-sided arrow. So there would be arrows at both points. A code of 1 would have the arrow situated at the first coordinate. A code equal to 2 would have the arrow at the second coordinate. Another option is to create the arrows such that there is no error bar appearance like in the book. And in this case, then, you could define the length of the arrows as 0, and then it's just a line. We could also plot this horizontally, and so in this case, then, we would simply invert the coordinates. Similarly, we would invert the coordinates within the arrows function. We can also create plots with more than one confidence interval, such as in this plot that we showed earlier. As an example, I will reproduce this upper plot, which is actually figure 7-1A in the text. So to create this plot, I'll create a variable to hold the difference in the means, where one difference in the means was 220 and the other was 152. I'll create another variable to hold confidence intervals for these two different difference in means. In one case, the confidence interval was, the upper limit was 409, the lower limit was 31, and for the other confidence interval it was 338 and negative 34. Now to create my plot, I'm going to use a horizontal plot. So the deltas will be my horizontal axis. My vertical axis will just be placeholders. I also would like to scale the graph for the plot so it will contain my confidence intervals. Okay. I can also add X labels and Y labels. If I'm not happy with this plot. And now I can add in my arrows. And in this case, my first coordinate will be delta minus confidence and delta plus the confidence interval. My length will be equal to 0. I can also add in V is equal to 0. And so I can see that with my lower difference in the means, which is 220, the 95% confidence interval does not contain 0. And thus, based on this sampling, the difference in the means is significant. However, in another sampling, my difference in the means was 152, but the confidence interval contains 0, and so the null hypothesis in this case is true, and we cannot say that there is a significant difference between the two means. I can also add in another line, which is the true or the actual change in urine production according to the graph, and in this case is 200. And I'd like to differentiate this by making it a dashed line. So the default is a solid line, but I'd like to change it to a dashed line. And so actually the line, if this LTY is equal to 1, that gives me a solid line. LTY equal to 2 gives me a dashed line. LTY equal to 3 will give me a dotted line, for example. And a 4 will give me a dot dash line. But you can put in different values to see what your different options are. So to review, we can use the confidence interval to estimate the size of the treatment effect. The confidence interval for the difference of the means is defined by our tolerance for error alpha, which then determines critical values of t alpha, and minus t, and plus t. The lower bound of the confidence interval is then determined by the difference of the means, the critical value t, the standard error, and the difference of the means. The upper bound of the confidence interval is defined by the difference of the means plus the critical value times standard error and the difference of the means. So what does confidence mean? Confidence is with which the true value lies within the interval. This true value could be the difference or the population mean, for example. We can also use the confidence interval to perform hypothesis testing, such that if the condition of the null hypothesis lies within the confidence interval, then the null hypothesis is true. Otherwise, it is false. We could also create confidence intervals for rates and proportions. So what does the following statement mean? The incidence of lung cancer is higher in smokers compared with non-smokers, with p less than 0.01. We can redefine the z-statistics for the difference of proportions to be the difference of sample proportions minus the difference in population proportions over the standard error difference of the sample proportions. Thus, when the null hypothesis is true, it becomes a standard z definition. Mathematically, this is seen or shown here, where the denominator is the standard error and the difference of the sample proportions, and in which we use the pooled variance of the proportion. If the sample size is large enough, the z-statistics will approximately follow a normal distribution. For a given alpha, we can get the corresponding critical value z alpha so that we can define the limits of our z statistic. So the 100 times 1 minus alpha percent confidence interval for the population, or the difference in the population proportions, is thus. Given the 100 times 1 minus alpha percent confidence interval for the difference in the population proportions, if the interval does not include 0, then we can reject the null hypothesis with p less than alpha. However, if the interval does include 0, we cannot reject the null hypothesis. We can also test a different hypothesis. For example, that the true population, or the difference in those proportions, equal to dp. The 100 times 1 minus alpha percent confidence interval for this difference is still this relationship. However, if the interval does not include dp, we can reject this hypothesis that the difference in the proportions is equal to dp with p less than alpha. If the interval does include dp, we cannot reject this hypothesis. We can also estimate the 100 times 1 minus alpha percent confidence interval for population rate or proportion. This approach is only valid for large enough samples. If not, then we need to use the binomial distribution. When the sample is not large enough and our p is very close to 0 or very close to 1, the z-statistic does not follow the normal distribution, but a binomial distribution. And in R, then, we can use the function binomial.test. The confidence interval can also be determined for relative risk. If you recall, the definition of relative risk is the number of cases over the total divided by the number of cases over the total between the two groups of exposure or intervention or no intervention exposure. The 100 times 1 minus alpha percent confidence interval for the relative risk can be estimated as, where we now need to take the exponential of the relative risk minus the z alpha times standard error, where this standard error then is defined as such. This can also be used to test the null hypothesis, in which the confidence interval is compared to a relative risk of equal to 1. Thus, if the confidence interval contains 1, then the null hypothesis is true, and the two groups are not different. They're from the same population. Similarly, we can define a confidence interval for the odds ratio. And remember, in our case, the definition of the odds ratio is this ratio here of the cases versus the controls. The 100% or the 100 times 1 minus alpha percent confidence interval for the odds ratio can be estimated as, and again, this is raised to an exponential, where you have z alpha and then the standard error in the odds ratio is defined as thus. We can also use this confidence interval to test the null hypothesis for the odds ratio. If the odds ratio of 1 is contained within this confidence interval, then the two groups are from the same population, and the null hypothesis is true.